So last chapter, we introduced the exciting concept of stoichiometry, and we're not done with that. We're going to continue to use that throughout the year. And this next chapter is really about more complicated stoichiometry problems. But before we talk about that, let's just discuss experimental error a little bit. You know, every lab report that we do, you guys have to determine where is the most likely place for experimental error. That has to be included in your lab report. And so experimental error is always there. We're human, right? We're fallible. Only God is perfect. There's always the possibility of mistakes whenever we do something. And so that's why I want you guys to think about that. But there are some things that we can do to help minimize experimental error in our experiments, right? And some of the things that we can do, there are a couple of things. One is make sure that the experiment is repeatable. So the more that we do an experiment, and we look at the results of that, if we can reproduce those results over and over and over again, then experimental error is minimized, right? The likelihood that we have a valid outcome to our experiment is very high because we've been able to repeat it multiple times. Another thing that you can do in order to minimize experimental error is to have others do your experiment. And so you've got to be able to repeat it multiple times yourself, but then you also turn it over to other chemists, scientists, right, that try the same experiment, and they have to get the same results that you did. And so this kind of helps validate our experiments, helps minimize the presence of experimental error. But the reality is experimental error is always there. And so I'm going to talk about a concept called percent yield. And basically, whenever we do an experiment in the lab, there's an expected yield, right? There's an expected amount of product that's going to be produced whenever we perform a particular chemical reaction. However, the reality is that the amount of product that we end up producing is usually, almost always, not the same as the product that we expected to produce. Now, the expected product produced is what we call our theoretical yield, right? So according to the math, when we run the numbers, we should be able to produce this much product given this much reactant, right, that we have. The amount of reactants that we have should be able to produce this much product. That's the theoretical yield. In theory, we should be able to produce that. However, there's the actual yield. There's the amount that we actually was able to produce in the lab. And so percent yield is basically a way to calculate the percentage of that experimental, the actual yield versus the theoretical yield. And so it is simply this: in order to find the percent yield for a particular experiment, we're going to take the actual yield, the actual amount of product produced, and we're going to divide that by the theoretical yield. And so when we do that, that's going to give us a fraction, right? A decimal, and then we're going to take that and we're going to multiply it by 100%, and that will give us our percent yield. So let's do a quick example in the book, example 8.1, just to make sure that we know how to do this. And in this particular example, I'll just leave this on the board. We should have plenty of room. In this particular example, we have a chemical equation where we take zinc and we're combining that zinc together with hydrochloric acid, 2HCl. The zinc, it tells us, is solid. The hydrochloric acid is aqueous. Just to save space on the board, I'm not going to write the phase on here. So we have this zinc chloride that is produced, and then also hydrogen, and the hydrogen is a gas. So aqueous zinc chloride, gaseous hydrogen. And it says the chemist uses an excess of zinc. So we've got plenty of zinc and 150 grams of HCl. So 150 grams of this, right? And when she collects the hydrogen gas, she finds that she made 3.9 grams of it. So 3.9 grams of this stuff, right? The question is, what is her percent yield? So she made 3.9 grams. How much should she have made? That's the theoretical yield. So given this number and the theoretical yield, we should be able to determine what the percent yield was. So how are we going to figure out the amount that she should have been able to make from this 150 grams. That's stoichiometry, right? So just to refresh your memory, I'll just write it up here. Remember, I showed you guys this. Grams of substance A to moles of substance A to moles of substance B to grams of substance B, right? That's the path that we have to take if we're going to go from grams of one substance to grams of another substance. So we got to do that here with the hydrochloric acid. We've got this many grams. How many grams should we have produced? All right. So the things that we need, we'll go to our periodic table and we will look at hydrochloric acid. And when we look at hydrochloric acid, we see that the atomic mass of hydrogen is 1.01. Chlorine, I believe, is 35.45. Let's double check that. It is 35.45 is the atomic mass of that. Adding those two numbers together, we get 36.46 grams per mole, right? That is our molar mass for hydrochloric acid. So 1 mole of hydrochloric acid is going to contain 36.46 grams of hydrochloric acid, right? So we're going to need that. We're also going to need to know the molar mass of H2. So let's calculate that real quick. H2, again, 1.01 is the atomic mass of a single hydrogen atom. When we multiply that times 2, we'll get 2.02 as our molar mass for hydrogen, right? And then finally, the other thing we need to know is that for this chemical equation, if we have 2 moles of HCl, it will produce 1 mole of H2, right? That's everything that we should need in order to calculate the percent yield, all right? Because that's what's going to give us the theoretical yield. So let's do that. We're going from 150 grams of HCl. And we're going to first convert that from grams of A to moles of A. So we got to find the moles of HCl. We're going to use this relationship for that. So we know that 36.46 grams of HCl is how much HCl we have in 1 mole of HCl. Okay, that's going to give us the moles of HCl. Then we've got to go from moles of A to moles of B. Our substance B in this case is hydrogen, H2. And so we know from this relationship right here that for this chemical equation, 1 mole of H2 is equal to 2 moles of HCl. Moles of HCl cancel out. So that gives us the moles of B. So we've gone from here to here to here. Finally, we want to figure out the grams of substance B. And so we're going to use this relationship. We know that there are 2.02 grams of H2 in 1 mole of H2. All right. So that's the value we're going to plug in our calculator. And when we do that, we're going to get 4.16 grams of H2. That's how much hydrogen gas we should have been able to produce, right? And so that is our theoretical yield. So plug in our numbers into our formula here. We produced 3.9 grams of hydrogen. That was our actual yield of H2. But we should have been able to produce 4.16 grams of hydrogen gas. We multiply that times 100%. And so plugging that in our calculator, we get a final number of 94, rounding 94%. That was our percent yield. Again, it's just a good reminder, right, that God is perfect. We are not. It's a good reminder of our need of Him. So that's why we have to calculate stuff like this, right? The best reminder in all of this is we all fall short of the glory of God. All have sinned and fall short of the glory of God. We need a Savior, right? So isn't it cool that even chemistry reminds us that we need a Savior? Thank God for sending Jesus Christ into the world. I'll see you guys on the next video.